Okay, let's take a look at question 4 in the sample exam 3. This question is about thermochemistry, specifically about work and heat relationship and how that adds up to delta E, something we discussed early on in thermochemistry. Let's look at the question. It says we have an ideal gas in a sealed container. So usually that means that the gas is in some kind of container where there's a piston that can move up or down. And originally this is at 4.8 atmosphere and 2 liter. And then it expands, as you can see here, which means the volume increases. So the piston moves up. The reason it expands is because the external pressure is 1 atmosphere. So since the pressure inside in the gas container is higher than the pressure outside, the gas will expand until the pressure is now equal. They're both 1 atmosphere. So we have pressure equilibrium. The expansion occurs at constant temperature. And it says that during the expansion, 7.5 kilojoules of heat is released to the surrounding, right? So it's coming out from the system. And then calculate delta E. Remember that delta E is calculated by adding heat and work that happens to the system. And we know the heat already in this case because we were just told that value is 7.5 kilojoules. The question is just what the sign of the heat is. Because the heat is released, then it should be negative 7.5 kilojoules or 7,500 joules. Now the question is calculating work. So work, the type of work that we talked about in chemical reaction is something we call expansion work, which is given by negative P external times delta V, right? And this really just means that the gases are expanding against some external pressure, which in this case is 1 atmosphere. And so we're trying to get the change in volume that occurs as the gas is expanding. So we need to find volume in the final state versus the initial state. Well, we know the initial volume, it's 2 liter. The final volume is actually here and we don't really know it. But we know that this expansion occurs under constant temperature and the gases are sealed in this container, so the number of moles also don't change. Now if you have constant temperature and number of moles, of course that means that Boyle's law applies. This is something we learned when we discussed the ideal gas equation. So if Boyle's law applies, then P1V1, which we can call the initial, should equal P2V2, or we can call the final in this case. Since we're interested in the final volume, we can just find the pressure initial, which is 4.8 atmosphere, times its initial volume, 2 liter, divided by the final pressure, which we said was 1 atmosphere. The atmosphere cancels out, and you have 9.6 liter as the final volume. Now that we have the final volume, that allows us to calculate the expansion work, which is negative P external, remember, is 1 atmosphere. That's how much pressure that the gases are pushing up against. And then 9.6 liter minus the original volume of 2 liter. And then this is in units of liter atmosphere, which is not going to be the same as the unit we have for heat. So we have to convert this, and the conversion factor is given in the question. It says 1 liter atmosphere is 101.3 joules, and that gives us negative 770 joules. The last step is to add the heat and the work, 7,500 plus 770, both in joules. So our final answer is negative 8270 joules, and that ends up being D right here.